Good morning.
Morning.
You're awake, that's good. Welcome to this talk about how symbols work and why we need them. My name is Anders. I'm from Norway. I work at Asinium, where we're a small startup designing a new CPU architecture, which I think is really cool. And I mainly work on the performance simulator and on the memory model, so I write a lot of C++ for that. I also run this website, cppquiz.org, and I just released this book, C++ Brain Teasers. So if you want something interesting to read on your way home, you can get that at the info desk for just £25, or get it online for this with a discount code that the publisher gave me. So yeah, I really like to talk about C++, but today we are going to talk about symbols. So how do they work, and why is this floor so squeaky? So in particular, we're going to talk about ELF symbols. So those are the symbols you find on Linux, and Windows has like some similar things going on, but it's not exactly the same. So don't try to apply this directly, but hopefully it can also be a good background if you also want to learn about Windows later. Who likes this term, C/C++? Boo, yeah? But this is a C/C++ talk. Actually, like everything here applies to both of these languages equally. So for once, this is actually a good term. And I've tried to keep everything to like the common subset of these languages, but there are some fancy C++ stuff like member functions and templates and like things we have in our superior language. If you have any questions about anything on the slides, please just shout out and I'll explain better. And if you have longer questions, please take those at the end. Today we're going to look at static versus dynamic symbols, binding versus visibility, and how do those relate to linkage in the languages, linking, weak symbols, unique symbols, how templates make things a bit different for symbols, and also inline variables, stuff like that. Where do these symbols exist, really? And how do you view them? Why do I have 3 symbol tables? And can I get rid of some of these symbols somehow, and what happens then? And finally, who gets a symbol? So which things in your program actually needs a symbol? And why would you why are you here? That's kind of the question, and why am I here? And like the most obvious reason to want to learn about symbols is if you're investigating linker errors, right? So you have like a duplicate symbol or a missing symbol or something. Or you can have more intricate things where actually 2 copies of the same symbol actually manage to sneak into your program somehow, and then like depending on which code path, you will reach different ones, and then you have all sorts of very hard to debug things. It's interesting when you're consuming libraries, you should know these things, and especially if you're shipping binaries, and especially if you're shipping libraries, it's important to know about these things. But most importantly to me, is I just think it's super interesting to understand how my programs actually work. So I can write the code, but like then what happens? And that's my main motivation for giving this talk here, actually. So we'll have one motivating simple example that we'll come back throughout the presentation to answer what are symbols and what are symbols for. And this is the small example we'll have. We'll have this values.c, or it could be CPP or whatever, where you have a global variable called value, and you have a function called getValue, which just returns that value. So that's a pretty simple thing we have in one file. And then in main.c, we have int main. It includes some header that hopefully forward declares this function, and then main just returns getValue. So when you run the program, you call main, and main calls getValue, which gives 42, and then the entire program exits with 42 as its exit code. In C and C++, we have a separate compilation model. So that means every C and CPP file in your project will include the header files and then be compiled in isolation. So when you compile one of these files, it can't see into the other file. So these are entirely isolated, and if you have like enough cores, you could, in theory, then just compile your entire program in parallel, entirely independently. And these then turn into object files. And object files contain a lot of stuff. I've tried to illustrate a couple of the things that go on in object files here. So in purple, I'm trying to illustrate the data section. So that's where the data goes. So if you have the value 42 here, and then 2a, that's hex for 42. So here's like the data from values.c ends up in the data section here, and then the code, I just made up some bytes here, I think, in green. And the same for main.o, you have maybe some global variables and some functions, like some data in purple and some code in green. There can be no dependencies between these because they're compiled in isolation. And yeah, maybe you also have like a library. Maybe it's your library, maybe it's a third-party library that also goes into your final executable. So eventually, you link all of this stuff into an executable that we just call the program. And then what the linker does, it just takes all the purple data section and just squashes them all into one big data section. And it takes all the text sections, that's the name of where the code goes. They take all the text sections and just squash them into one big text section. And then you have your executable that you can run with both code and data in it. But there's one issue for the compiler. When the compiler is compiling main.c, it needs to emit some machine code to call getValue. But the compiler has no idea where getValue is because the compiler can't see into this file, and it doesn't know where the linker is going to place it in this file. So it's actually impossible for the compiler to generate a call to getValue. So maybe the linker can help us a bit later, and we'll look at that later. But so far, like, it's not possible to do this. Let's have a closer look at values.o. I just want to look like what's in there. Let's see how we can investigate our binaries and learn about them. And one very useful tool for that is objdump. And you can do many things with objdump. Maybe this, like, most basic thing is just do -s to just hex dump the thing and see what's in here. With some metadata, so it says, well, file format is ELF64 x86-64. So we are an ELF binary, and we're on an x86 64 system. So this was made on my Linux machine at work. And then it says, here's the contents of the text section. And the text is where all the machine code goes. And then it has the offset here. And it says, like, here are the bytes. And I happen to know that this is actually the push RBP, and this is the ret instruction. So that's the very first and very last instructions in the getValue implementation. So the text section only has like the raw code that goes on your CPU and nothing else. And then it says, here's the contents of the data section. Again, at offset 0 in that section, we have the value 2a, which is hex for 42. So then we can start like learning a little bit what's inside here. That's not the most useful way. Quick question here.
And the data are both at the same address?
Yeah, the text and the data are both at the same address because this, and that was the question, and the offset is relative to the section. So the 2a here is at offset 0 in the data section, and the beginning of the getValue is at offset 0 in the text section. But yeah, so you can't learn a lot from this, but it's like a nice starting point. A better thing to do is to pass -d to disassemble this. And then it again says, here's the file format, here's the text section, and here's the getValue function. So it's telling me here's the getValue function, and here are the offsets of the instructions. Here are the bytes again, the same bytes that we saw on the previous slide. And then it's showing me the assembly code. And there's no assembly code in the object file, it's just the machine code, like the raw instructions that go on your CPU eventually. But objdump is then able to translate this back into assembly so we can understand actually, okay, so what are these instructions, and not just look at the bytes. And it can also show me the name of the function. But the text section only has the bytes of the function, it doesn't have the name. So it's able to display that here. So maybe then it's becoming obvious that there's some sort of table of symbols somewhere that can tell you where are the things inside of these sections. So let's look at the symbols. And objdump has a -t option to list all the symbols. So if I do that, again, it has some header here. And then this is easier to read from the right to the left. So it says we have two symbols. The first one here is the value symbol. It is 4 bytes big in the data section. It's an object, so as opposed to a function, it's like a variable, it's an object. It has G for global binding, which we'll talk a lot about later, and it's at offset 0. And then we have a symbol getValue. it's C, big, it's in the text section where the code goes, and it's an F for function, again, global binding that we'll get back to, and also offset 0. So we can see these offset of these symbols are also relative to their respective sections. Who uses objump to list their symbols? A few? Ha, I don't. What do the other guys use? Readelf, yeah, or NM. So NM is what I typically just used to use before I started really poking at things. So I can use NM as well on values.o and see that we have get value. It has a capital T for text section, and value is a D for the data section, and again the offset 0. I can also run objump on my main.o. So remember, main is just calling get value, and then let's see what kind of symbols do we have in main.o. And we have the main function itself. It's 10 hex big, and then in the text section, it's a function, global binding, offset 0. And we also have a symbol for get value. And this says und for undefined, because in main, we need the symbol. We're going to call that function. We don't have that function in here, so we just have a note here that we're going to have to find this somehow when we link. I can also run nm on main.o, and then we have a T for main for the text section, and the capital U, which means undefined, because get value is not defined here, but there's a reference to it, so we're going to need it later. And yeah, all of that information about the symbols and their sizes and everything is off in a different section called the symbol table. So this is not intermixed with the actual machine code or the actual data. It's in a different place. So we've been mentioning quite a few sections now. Let's look at which sections we actually have in values.o. And then we'll use readelf, that someone suggested over here. We pass it -s to just list the sections, and -w is just to have a bit wider output, which formats it more nicely. It says there are actually 20 different sections in here. And we're not going to read through them all, but we can see we have the text section for the code, the data section for the global data, and symtab. So that's a separate section where all the symbols are stored. So this is then where you have like the symbols, and it just has like pointers into the other sections telling you where to find all of these things. Okay, back to this thing here. So we mentioned that when we're compiling main, we don't know where get value is. So it's impossible for the compiler actually to generate a proper call instruction that calls get value. But later, the linker is going to link all of this stuff into the executable. So the linker knows, okay, so where am I writing this section? Well, I'll put that down over here. And then it can look at the symbol table and see, okay, oh, so where in this text section is get value actually? So then it takes, like, where is it and what's the offset to get value? And now the linker knows where the function is. So maybe the linker can help us to resolve this problem that we have. And let's look briefly at that, how that works. That works with relocations. And last year I had a talk that went much more into detail about linking and relocations, stuff like that. So I'll put a link to that at the end. But I'll go over it briefly here. So again, I do objump-d to disassemble my main.o, where we have this problem of finding get value. And I also pass it -r to show the relocations. And yeah, -m-intel is just to use the Intel assembly syntax, which I find easier to read. I'll have a link at the end also to a talk about some introduction to assembly. The interesting thing here is this call instruction. So the compiler at least managed to write out a call instruction. And E8, that's the call instruction. You can see this at offset 9. You have these bytes to it as E8 for the call instruction. And then it just gave up and put zeros. Like, I don't know where the symbol is, so I'll just put zeros. But I'll also put in a relocation. And a relocation is a note to the linker saying, like, when you link this stuff, can you please figure out where get value is? And then, like, just fill it in at offset A. So this is offset 9, here's offset A. So the linker will then just check, okay, get value is at this and that address, compute the distance to it, and just fill it in here. So then the linker doesn't have to understand like machine code or assembly code or anything. The linker just needs to know that, well, I need to compute the distance to get value and put it at this particular address, and it doesn't need to understand anything else and just fill it in right over here. Yeah, the relocation itself is not, again, intermixed with the machine code. The machine code is just the bytes that go on your CPU. So all the relocations are off in yet another section. And an objump is just able to then inline that information here, just like it disassembles the stuff and inlines the assembly code for us here, so everything is easier to see together. And when the linker gets around to linking the executable, it loops over the relocation table for main.o. It might have like several things that the compiler couldn't find. And all of those are in the relocation table, so we can just loop over that. And then we can look in the symbol tables in other object files, like get value is in values.o. What's the offset for that function in there? And the linker knows where do I take this machine code section and put it in the executable. So then it can compute the final address of get value and just fill it in at offset A here, where these zeros are for now. So finally, we have linked our entire binary, and we can objump that as well to disassemble it. And then we can see here the call to get value. We still have the opcode for call, but now there's an actual distance to jump here. So the zeros are gone. We now have resolved the final address. So nothing needs to happen at runtime other than just like jump over here. You don't need to like look anything up or anything when you execute this instruction. Yeah, and the relocations are also gone at this point. And finally, we can also happen to notice that main is no longer at offset 0, like it was in the object file. It's now at offset 606, because when you link the executable, you get other stuff added as well. So like the underscore start and like the libc stuff that happens before main is also in here. So now you get more bytes in there, and main is no longer at the beginning. Let's see what happens if you don't have any symbols. And I never remember how to call the linker, so I just ask GCC to link for me, and it will call the linker. So I say GCC-O, can you create the program as an executable from these two object files, values.o and main.o. And the linker says, fine, I'll do that. Then I run the program, and I finally can see that indeed we do exit with the value 42. So our program works. And it worked because if I run nm here on values.o, because I have these symbols, so the linker was able to find them. But I can strip away the symbols. So strip is a tool that can remove various things from your binaries, and without any arguments like this, it will just strip away the symbol table. And that's easy, since the symbols are not intermixed with the machine code. It's just a section. You can just remove that single section. So that's an easy job for strip. If I do that and run nm again, now the symbols are gone. But the code is still there, right? The text section and the data sections in values.o still have the function, still have the value. It's just that we don't have any symbols anymore to look up where they actually are. And if I then try to link again, I get this good old undefined reference to get value that you have probably seen every time you forget to add the definition somewhere. So now I can't link, and now we understand a bit more like how does that process actually work? How can the linker give you this error message? The story so far then is that we have a separate compilation model. We have sections like data, text for the code, symtab, and so on. Text only has the machine code. Data only has the data. And then symtab is a table of symbols pointing into these other sections, telling the linker or yourself where your things have ended up. We saw how the compiler can't find a function, so it just fills in zeros and add a little note to the linker called a relocation in a separate section yet again, and the linker can then fill in these relocations when linking. And finally, we saw that we can't link if we don't have any symbols. Yeah, still trying to keep it a bit cross-platform or cross-language. Are there any C programmers here? Half a C programmer. Okay, like could have done everything in C++, I guess. Right, next up is linkage. So again, cross-language concept of linkage, I figured I need a little helper function here. So if I just have the get value function return the value directly, that's a bit too simple. So I add a helper function. So get value calls helper, helper returns 42 out here, and then get value eventually then returns 42. And then I put static in front of my helper function. And what does static mean in this context?
It overrides extern and makes it effectively hidden.
Yeah, it kind of hides this function. That's correct. So it gets internal linkage. So the same will happen if you put helper in an anonymous namespace. You get internal linkage. And that means only this file. So the compiler will compile this file, include the header files, and then this helper is available to all of that in what we call the translation unit, which is like the C or CPP file with all the headers included. But it's not available outside. So no one else in other files can link to this function later. So it has internal linkage. And if I run nm again, I can see get value and value are still the same. And then we also have helper. It's also a T because it's in the text section, it's code, but it's a lowercase one. And the lowercase means it has internal linkage, is hidden to this, hidden inside of this translation unit, not available to anyone else. So in C and C++, we have linkage. It's just like an abstract concept of the language that tells you about these things. And then value and get value have external linkage, and helper has internal linkage. And the way this actually works is then in implementation details, right? On Linux, we have elf binding. On Windows, they probably have something else. And elf binding is then like a concept in elf. That's separate from linkage. Linkage is a language concept. Binding is the elf implementation detail. And elf then uses global binding for like globally visible symbols and local binding for things that's local to the translation unit. So there's a very simple one-to-one here between external linkage and global binding in elf. And then importantly, nothing changes in the text section. So whether I put static or not here on the helper function, the generated machine code looks exactly the same. It's just the symbol table that has these details. Yeah, so yeah, this is the same code as on the previous slide, just moved it to the side a bit. And then in main, I also needed some helper things. So if people don't give me the right command line arguments or whatever, I have this helper function to just print some help text. So now I have two helper functions. And like normally, if you have two copies of the same symbol, you can't link because you have a duplicate symbol. But since both of these have internal linkage, they both have local binding, and then the linker is happy and it won't actually look for these in other data sections or text sections when it's linking this, because it's just internal anyway, so you're actually allowed to have many of the same symbol, and the linker just doesn't care. And the same would be if you put these in anonymous namespaces. And yeah, and then like this is, I guess, what everyone is used to doing, but now you understand like why does it work the way it does. Yeah. There we go. Yeah.
Is that would be the same as if you put it in an anonymous namespace? Is it then also internal linkage?
Yes. If you put it in an anonymous namespace, you get an internal linkage and a local binding. Yeah, because the anonymous namespace hides it inside of this translation unit. So then you can have like as many foos you want in all your project. As long as you define it in the CPP file. Because what happens if I put these definitions in the header file? I go into value, so I move the definitions up into values.h now. So value equals 42, and here's the body for the get value function. And then I include values.h in many of my implementation files. Then the compiler will like just copy paste the include files, right? That's what it does, and then compile it. And now we have multiple definition of value, multiple definition of get value, because now these definitions actually exist in all of the files that included the header file. So then we see how that works, how can the linker tell you this, and how you can use nm to debug this. And the classical solution to this is then to make sure you don't put the definitions in your headers. You put only your declarations. So you turn value here, say extern int value, and you just put the forward declaration of this function, and then you move the definitions down into a single implementation file. Since then when you link, you'll only have one of these symbols. And still, over in main.c, I've seen the declaration of that function, so I can generate code to it, but still, I don't know where it is, so I put the relocation for the linker to resolve. Okay, so let's do some C++ only stuff, since it's a C++ conference. So we have a really fancy feature in C++ that your structs can have functions in them. Pretty cool. So here is a member function in my class. I have a class some class with a member function called getValue. And you can choose whether to put the definition inside of the class definition in the header file, or whether to put it down into your implementation file. But doesn't that mean that everyone who includes values.h now will have the definition of some class : getValue? Well, what's going on now? And we have templates. So here's a template called getValue, where you can choose the type, so we can get this one as an int or a double or a long or whatever you want, but specifying the t. And this has to be in the header file, right? Because when I instantiate this in my implementation files, I have to have the definition there so I can substitute in the correct types and everything and instantiate this function template. So then again, I should get conflicts, because everyone who does that will have the definition for this function. Yeah, so if, for instance, in values.cpp, I have a function called useIt, where I use getValue of int, and I also just make an object of some class and call the getValue function. So now I use both of these things, and I will get code for it. And how does that work? If I run nm again, and -C means demangle. So show me the nice C++ names. Don't show me the strange mangled names that you get otherwise. And we can see that useIt still it's a normal function. It's a capital T text section global binding kind of thing. And then we have W for the other ones. For the function template and for the member function, we have a W. And the W means it's a weak symbol. And a weak symbol is saying you have the definition here, but you can have many. So if you're linking and then you have like 12 object files with the same definition, you can then just, the linker will then say, I'll keep this one, and I'll just discard the other 11. So everyone uses this single one, and you're allowed to have many of these. But they have better be the same. Okay, so normally C++ says you can only have one of each thing in your program, right? It's called the one definition rule. You can only have one definition of all of the things. Except if it's like a template or a member function and stuff like this, then you're allowed to have many. But if you have many, they must be the same. Otherwise, it's an ODR violation, a violation of the one definition rule, and that's undefined behavior. Imagine in the getValue function template, if I had an ifdef. So ifdef new version return 2, else return 1. And then in my CPP files, in some of them, I set the new version define before including the header file, and in the other ones, I don't. So sometimes when I include this header file, this is supposed to return 2, and other times it's supposed to return 1. And then like the linker discards all of these except 1, which then returns either 1 or 2, who knows? And then of course, that's undefined behavior. So if you do stuff like this, you have to make sure they're the same, otherwise you're in violation of the one definition rule, and then UB happens, and then everything can go bad in very interesting ways. And yeah, one final thing. I get these symbols here, these weak ones, because I use them. So if I didn't use the function template, if I didn't call the member function, then I would not actually even get symbols for them, and the compiler could even just not emit code for them. So you don't, even if you include a header file that has some definitions, you don't necessarily get those definitions in all of your implementation files.
If the function is inline, do we still get the symbol?
Good point. This is probably compiled in debug or without optimizations. If I compile with all 1 or more, these will get inlined, and then I don't get the definitions in here, because anyone else who needs these will also have included this header file, so these symbols will then be there. Yes, stat functions are very similar. I'll mention static member functions later, but they. Oh yeah, the same for static functions. So if you like the static or the anonymous namespace function, the question is, do you get code for those? Not if they're inlined, because you inline it, so it's no longer needed in this translation unit, and it's not going to be needed anywhere else either, because anyone else who needs it will also have. Oh, for the static one, it's only in this anyway. So yeah, if it gets inlined, the compiler won't bother even writing out that function. Yeah, so weak symbols is what you use, and they have to be the same. That's where we were. And you can also manually use weak symbols if you want. So we didn't tell the compiler anything about like this function template is weak or this member function is weak. We just said language, right? And then the compiler decided to use weak symbols, but we can use them manually for some cool things as well. So I want to complicate my library even worse, and I want to introduce some resource loading thing. So instead of just getting the value, you can now load a resource, and the resource will provide you with the value that you're looking for. So I declare here a load resource in the header for my library. And somewhere in the implementation of my library, I have a definition for load resource, which gives me a resource pointer. And then my users can call the load resource function to get the resource struct, and then get the value from the resource. Okay, so this is a thing I can do. But what if I want to allow the users to override the resource loading? So I compute this value on OpenCL, but I want my users to be able to compute it on CUDA if they want. Or I get it from a file. I want to allow my users to load this from like an embedded SQLite database they ship with their product or whatnot. So I want to allow them to override the resource loader. And then I can manually mark this as weak. So I can say attribute weak, and then here's my function. Now this will turn into a weak symbol. And now this is not standard C++ anymore. Now we're ELF specific here. But that's a thing we can do. So now this will manually turn into a weak symbol. And my user can then also declare a load resource function, which would normally be like a conflict, right? But they don't mark theirs as weak. So theirs now has global binding, whereas mine has a weak binding. And what the linker does then, it's going to say that, well, you can have as many weak symbols as you want, but if there's one global symbol, that will take precedence. And I'll discard all the weak ones and just keep the single global one. You still can't have more than one global, then there's an error, but you have one global that overrides all the weak ones. So now, when the user calls load resource, it's actually their load resource that will be called instead of mine. And then they'll get their value like that. And yeah, so if you run nm on values.o and main.o, we can now see that in values.o, which is the thing that goes into the library that we're shipping, we have a weak symbol. And in main.o, we have a global symbol. So that's how you can make sort of a little plugin system kind of thing for static linking. Everything is still only static linking here, by the way. Right. Another thing that complicates things a bit is inline variables. So in C++17, we got inline variables. So now I no longer have to put all my definitions down in some CPP file somewhere. I can just say, inline int global value equals 1, and I don't have to bother like putting it down somewhere else. I can also have static class members, mark them as inline, and just put the value in there and not bother with these like moving stuff away. Yeah, and I also have just a static member function just to get at that value. I'll use that later. So how does this work then? Well, in main, I now return, as we've seen before, I'll just use this global value, and I'll call this static member function. That gives me the static member object here. So I'll just use both of these. And now if several people include this header file, you will get duplicate definitions again. So how does this work? How do they fix it in 17? If I run nm, main is a normal global thing. the member function, even if it's static or not, so that was the question earlier, static member functions, normal member functions, it's just a function. So it gets a weak symbol because it has the definition in the header file. And then we have a lowercase u. And the lowercase u means a unique symbol. And unique symbols are a GNU extension to ELF. And that's how they decided to implement inline variables. And unique symbols are kind of like weak symbols. You can have as many as you want. The only difference is you can't override it with a global one. So if you have a bunch of unique symbols, all the other ones also have to be unique. They can't override it like we did with the resource loading thing. So this is just for like implementing some language features like inline. And yeah, one more thing. We saw that when you use NM, you have the capital or lowercase t based on global or local in the text section, capital or lowercase d based on global or local data section. So you have the lowercase u for unique symbol and uppercase u for undefined symbol. Like these are not related at all, so that convention breaks down here, so it can be a bit confusing. Just something to be aware of. So let's say we have a class with the definition of some member functions in header files, and we try to link several object files that's using these member functions. And we have all of these weak symbols, and I said, well, the linker just throws away all but one. But maybe you have some questions. At least I had some questions. I thought the linker just copies sections from object files into the binaries, the executable or whatever you're linking. We saw that on one of the first slides. It takes like the entire text section, copies it over that way for you. And this section just copies it over here, entire sections. So how can it remove a single function or a single object out of those sections when it's deciding to pick only one of the implementations to use? And it can't. It's not possible for the linker to just remove single things out of these sections. So how does this work? Let's try to figure out how it can remove these things. So let's just run objump and list all the sections in main.o. And I just grep for the .text, which is the text section. And it says, yep, here's the text section. And here are also the text sections. And you can't automatically demangle these, but you can see here, this is text.someClass : getValue, and this is text dot getValue of int. So what the compiler did was actually to create an entire new section for the member function and an entire different section for the instantiation of the function template, just to allow the linker to be able to throw away all but one of each. And when we said that, at a few occasions we've talked about the compiler not generating stuff if you don't need it. So if you don't instantiate this template, you don't get an instantiation. If you don't call the member function, you don't get this generated either. So you don't get all of these extra sections unless you actually need them. So yeah, the same happens for inline variables and for templates and member functions. Everything that's defined in a header can be solved like this. So in summary, for binding, in C and C++, we have external and internal linkage for the stuff in our translation units, implemented with global and local binding on ELF. Then we have weak and unique binding for symbols that are defined in headers, such as member functions, function templates, inline variables. We saw that we can actually manually put attribute weak in front of something to turn it into a weak symbol. And how the linker uses one section per weak and unique symbol so that it's able to throw away duplicates when linking. Right, that's it for binding. Now, dynamic linking. I have to talk about that as well. Static linking is simple, kinda. Dynamic linking is much more complicated. The C++23 standard is 2,124 pages long. And I'm sure the C standard, I don't read it, but it's also probably pretty long. So how many pages out of these is needed to describe the dynamic linking? 0? That's very few. And that's correct. C and C++ do not know anything about dynamic linking. So if someone has ever told you, I have a DLL for you, I have an SO file for you, they're lying, they don't exist. Okay, all of this is vendor specific. And that's a bit unfortunate because it leads to interesting questions around like ODR rules and SO files and stuff that at least I haven't been able to properly figure out. But let's see how it works on Linux on ELF. So we have this same example again that we had before. Main, but we're making an SO file now. Instead of linking an executable, we're linking an SO file. So now we're creating the shared library. We're not consuming it yet. We're not linking to it. We're actually just making it. And making it is exactly the same as making an executable. So I just renamed my main because now this is going into an SO, so we don't need a main. So I have some other.c, and this one keeps dropping out. Yeah, you have an other.c, which then and values.c turn into values.o, other.o. You have a static library again that also gets included, and you create this dynamic library. And I think I already have used several terms because there are a lot of terms. So you have dynamic library, shared object, dynamic shared object. Some people even say DLL on Linux, even though that's like the Windows thing. The proper term on Linux is dynamic shared object. So I'll try to stick to dynamic shared object or shared object for these. So everything we have learned so far is still true when you're creating the shared object. So the question is then, like, what do you do with your API? Because there's going to be a lot of stuff going into your shared object, and only a little bit of it is going to be on the API that you want customers to use, and the rest you might not want to allow them to access. Because, like, one thing, you don't want people to accidentally discover an undocumented function and start relying on it, and then they complain when you upgrade and it's no longer there. And you say, well, it's not in the documentation or in the header file, and they say, well, it was there in the SO file. And then you have some angry people shouting at you. Or maybe there's some secret stuff. So you can't like really hide it that well, but you can add a little layer of security by obscurity if you don't include like the options to actually link to those things. And since all of this is needed at runtime, like when you start a program, it loads some SO files. You have to actually then resolve all the symbols across all these SO files before you can use them. So it would be nice if you didn't then have to look through all the symbols, but only the ones that are part of your API. So let's see how you can do that. So here's a shared object I'm shipping to some users. It has an internal function that only I'm allowed to use inside of my SO file, and then the API function is what the users are supposed to use. And here's the implementation. Internal function returns 1. API function calls the internal function and multiplies it by 2. And here they're both in the same file. Like in reality, these could be in different files, and they would still have to be able to call each other, right? Just like any static linking, you have to. All your functions in the different object files must be able to call each other. And then we can see, like we've seen many times now, I just list the symbols, and both API function and internal function have a capital T, so they have global binding, external linkage. But I want to limit this, right? And if I also then run nm on the SO file, they both have still external linkage and global binding. So how can I, what can I do, right? I can't give them internal linkage, because if these are in different files, when I create the SO file, when I link it, they have to, all my functions have to be able to call all the other private implementation details. It's just, I don't want to expose it outside of the SO file. So I can't use linkage and binding for this. Hello, Eleanor. Visibility versus binding. Yes, sorry, I get easily distracted. Yeah, so how do you expose, control the symbols that get exposed in your DSO? You do that with visibility. And visibility is a completely different thing than binding. Binding says, can this symbol be used outside of this translation unit? And that matters when you're statically linking things. Visibility says, can this symbol eventually be used outside of the shared object when people link to the shared object? So that matters for people who link to it, okay? So binding matters when you create it, and then visibility when you link to it later. C and C++, well, they don't know anything about dynamic linking, so they don't know anything about visibility either. So this is vendor-specific stuff. On Linux, we have visibility. And then we have default versus hidden visibility. So default visibility means it's visible to everyone. Hidden visibility means it's only visible inside of this shared object. And you can control that by putting attribute visibility default or hidden. Or you can actually pass a compiler option, f visibility equals hidden, then all of your symbols get hidden. So like your API is empty. There's nothing for the user to link to. And then you can override the ones that you actually do want to expose. And the default is default visibility. So it's a bit unfortunate naming. Default visibility means it's visible. And then like the default option for the visibility option is default visibility. So default kind of means two different things. I will mention a little bit of Windows actually in this section. On Windows, you have a different thing. You have the decal spec thing. I'm not a Windows expert, but if you want to export something from your DLL, you have to prefix it with the decal spec DLL export. And then when you use it, you're apparently supposed to prefix it with decal spec DLL import. So you have this, like, depending on whether you're using it or creating it, you have to put these things. And I'll get back to some tricks for that. So let's see how we can control visibility. You want to use your build system for this. So I'm using some CMake stuff here. I'm making a shared library called dinlib from probably many files, but for instance, library.c here. And then I set the compiler options for dinlib to include fvisibility hidden. So now every time I compile something that goes into the shared object, they have fvisibility hidden. And this happens at compile time, not when I link the shared object, it's when I compile the object files that eventually go in there. That's when I have to control it that early to set the visibility. And then I can put this attribute visibility default in front of my API functions. So I just put those in the places where I actually do want to expose something. And I could have done it the other way around. I could have not passed fvisibility hidden, so everything is visible by default, and then just put attribute visibility hidden on the stuff I want to hide. I don't want to do that because hopefully I have like 2,000 functions in my shared object and I want to expose 23 of them. I don't want to type that on like all the other ones. There's less typing if you do it this way around. And it's very easy to forget to hide something. It's much harder to forget to expose something that's on your API because then all your tests are going to break. So I prefer to do it this way around. Except I don't like all this typing, so I will make a macro like this. So I'll define DSO export, and you probably want to prefix this with your company name or something to not conflict with other people's libraries. So you do make some define like this, DSO export, and then I can just put DSO export in front of everything I want to expose from my API. And let's do a little cross-platform slide just because it's useful. So I said on Windows, you have DLL export and DLL import. So when I have a function, I make the DLL. The header file where you declare this function has to say decal spec DLL export. And then in the header file that the user uses, this function has to be declared as decal spec DLL import. And very often, it's the same header file, right? The same header file that goes into making the DLL, you just ship that later together with the DLL. So now like this header file has to say DLL export when you make the DLL and DLL import when you link to the DLL. So that has some complications on Windows. So here's what I think people tend to use. I think this is from an example from GCC documentation somewhere. So if I'm on Windows, I have this new define called building DLL. So when I'm building the DLL itself, I set this building DLL define. So that means DSO export now means decal spec DLL export. And when the user links to my DLL, they don't set this. So this would also then be prefixed with my company name or something. And they will then not set this. So now the same macro means DLL import. So then the same header file can be shipped to the customer, and it means the export import depending on whether you're building the DLL or whether you're using it. And if you're not on Windows, you just do what we already saw for Linux. You just say DSO export means attribute visibility default. So it's simpler. So we've been using nm quite a lot. Let's try nm again to see what's the difference between the API function and the internal function. And you can't see anything. They both have global binding because they have external linkage. So like you can't see the visibility here. So this time you have to use something else. For instance, readelf to list the symbols in library.o. And now you get more information. Because now you can see, well, they both have global binding because they have external linkage. Everything can find each other when you build the library. But visibility is different. This one has hidden visibility, and this one has default visibility. So now you can see these are two different concepts that go in the symbol table. And if you continue to run the list of symbols on the SO file after you made the SO file, like linking is done, the SO file is finished, ready to be shipped, and you can see now we have two symbol tables. So we have the sim tab at the bottom, which is the same as before, basically, but you have a new one called dinsim. And in dinsim, we only have the API function. The internal function isn't even in the dynamic symbol table with like hidden visibility or anything. It's not even there. So now you have two symbol tables. So why do I have two symbol tables? Couldn't I just put binding and visibility in the same symbol table and use that in both cases? And we saw here that, well, you do actually have both of these in the sim tab. So why duplicate half of that info, or hopefully not half, but at least the API surface, so like 5%, why duplicate that into yet another symbol table? And the dynamic symbol table is needed at runtime. So when you load your executable, it loads some SO files that maybe load some other SO files, and everything has to be able to resolve everything that's in different SO files. So we need it at runtime, and yeah, that's what I just said. And then it's nice if this table is small to look up in, and like your binary gets smaller as well. You don't need to ship all the things you don't need, and it's quicker to look up in a small table than in a big table. And the static symbol table can be removed. We saw that earlier. If you remove the static symbol table, you can't link anymore. But if you make an SO file and remove the static file, well, linking is already done. Now it's only dynamic linking left, and that only needs the small dinsim table that has your API symbols in it. So you can get rid of all the static symbols, shrink the binary a bit, add a little bit of security by obscurity, and yeah, that's what you can do with strip. But there are more symbol tables as well. Like you also have debug symbols, and I'm not going to cover the debug symbols here, but those are huge because those don't just say get value that address. They say get value over here, you got it from this file, and it's on this line number, and the weather was so and so, and like all this extra data you have in the debug symbol table. So that can also be stripped away. Yeah. So now we have seen why we need symbols, how they work, and what you can do with them. But we haven't really talked about who gets a symbol, like which things in my program actually need symbols. So let's finish off the talk with a little game of who gets a symbol. So here's the first question. I have a global variable and a normal function. So which of these things get a symbol? Both? Yeah, I get a data symbol for the data and a text symbol for the function. And then we saw, what if I give them internal linkage with static? Who gets a symbol now? Well, it depends. If I use them, I get symbols. Then I get a lowercase d and lowercase t for internal linkage data and text, respectively. And if I don't use them, no one else can use them because they have internal linkage, so the compiler won't output code, won't output symbols for these, and I don't get symbols. So I get lowercase ones if I use them. Now my function has a parameter and a local variable. So do I get a symbol for the function? Do I get a symbol for the parameter? And do I get a symbol for the local variable? I think someone said only the function, and that's correct. Because when I link, I have to find the function. It's one function. It's over here in the text section, everyone needs to find that function. But like the parameter and the local variable, they just pop in and out of existence. Every time you call this function, the stack grows and you get the stack frame with this, or maybe even in a register. And if you have like a recursive function, you can have many of these. So it's like, it's not one thing. It's not something you want to link to. You just find them wherever the function, the stack is, you just find them relative to the top of the stack. So these don't need symbols. What if I put static in front of the value? So now this has static storage duration. Now static means something different. It means it's only one value in my program. Lowercase d is correct because now there's only one value. Every time I call this function, I don't care about the stack. Every time it's the same value. If I increment it one time, that value should still be incremented the next time I call this function. So yeah, this one you need a symbol for because it doesn't go on the stack. It goes in the global data somewhere, and everyone has to be able to find the same thing. And it's lowercase because no one else is supposed to be linking to this. And if I compile with optimizations, since I don't modify it, this is probably just content folded and inlined, and then you don't get a symbol for it. Final example, no, next to final example. I have a class. Does the class get a symbol? Does the class member get a function? And does the member function get a symbol? Just the function? Yeah. So the class doesn't really exist in my program. Like the class isn't a thing anymore after compilation. You only talk about members. You never like call the class. Like it's not a thing in my program. So we don't get a symbol. You don't get any code for the class itself. And the data member is exactly like any other local variable. Every time you put an object on the stack or on the heap or something, it's just like some offset inside of the address of the struct or the object itself.
Generate the function.
Oh, so
Why not generate the function like this? Do they get symbol?
yes. So if you have like the compiler generates a copy constructor or a destructor or whatever, then those get symbols because people have to call these. At least if they're not trivial. If they're trivial, you don't need to call them, and then probably you don't get any code generated. I would guess. But otherwise, you do have to get symbols for this. And the member function here, you get a W if you use it, because it can be included in many files. This is the final one. Now I made my member function static as well. So same example as previously, except that the member function is now also static. It's a class function rather than like an object kind of function. I think I forgot something, but anyway, the point is that the function is a function. It's still always one function. It doesn't matter if it's like a member function or a static member function. It's always only one implementation of this function. It lives somewhere in the text section, so it has to have a symbol. But as we saw before, it's weak unless you, it's weak so that you can disambiguate. The linker can do that. And the member here is not defined. It's only declared. So actually, it's undefined here, and until I put like struct : member equals 42 down here, it's undefined. So to summarize, who gets a symbol? Only things there are one of. Things you need to find the single thing of, like a global variable, a function, and so on, then you have a symbol. Like local variables and stuff, you don't need symbols because they are just on the stack or on the heap, or like you have a pointer or a stack, top of the stack or whatnot. If a symbol has internal linkage and is inlined, it's omitted. You don't even make code for it because it's internal, no one else can link to it anyway. Yeah, and if a weak or unique symbol is unused, it's also omitted. And that's it for who gets a symbol. So to summarize, for the entire talk, we had a separate compilation model and relocations to be able to find things for the linker. The linker then uses symbols to resolve all of these things. External and internal linkage in C and C++ is implemented by global and local binding on ELF. Weak and unique binding is used for symbols that have to be allowed to exist in many. And be aware of the ODR rule, they have to be the same. For shared objects, we use visibility since we can't use binding. And that's controlled with the fvisibility compiler option or attribute visibility. And so we have sections like data, text, symtam, dinsim, and we have some rela sections for the relocations. And that we can use nm, objump, and readelf to look at these symbols and disassembly and all that cool stuff. And that you can use strip to remove the static symbol table, for instance, and also the debug symbol table. And finally, we saw that only like singular things get symbols. That's the end of this talk. And if you want to learn a little, like if you don't know assembly from before, this is a talk about like an introduction to the kind of assembly that's relevant for this talk. Like how do you call a function, how do you return values from functions, stuff like that. x86 specific, that one. And this other one, what happens after the compiler, is the same talk I had here last year, going into much more detail about linking and relocations and stuff like that. So with that, I say thank you for attending this early in the morning.